Good morning to one and all. I am Dr. Vaisya Taramaro, Associate Professor, Department of Mechanical Engineering, Gayatri Vidya Parishad College of Engineering, Visakhapatnam. Today, I would like to give the lecture on the keys in the design of machine members 1. So in this case, we will discuss about the definition of the key and the different types of keys, and how do you find the torque in the rectangular sunk keys, and what kind of stresses are developed in these keys that we will discuss here. The key is generally the device which it can be used for connecting the two machine parts like the shaft with the gear, and it can be used for connecting the shaft and the hub, and in general the key can be used to transmit torque from one shaft to the another or the pulley here. So the primary function of the key can be used for to prevent the relative motion between the shaft and the connecting members of the machine, means it will be gears or the pulleys or the sprockets here. So it is always inserted parallel to the axis of the shafts. These are used as the temporary fastenings, and it can be subjected to the mainly crushing and the shearing stresses here. The keys are generally made from cold rolled mild steel, and these are generally based on the shaft diameter here. Coming to the different types of keys, there are several keys are there, but from the subject point of view, the important keys are the saddle keys, sunk keys, and jib-headed keys, feather keys, and the woodruff key, round key, or it is also sometimes calling as the pin and the splines. So coming to the saddle keys are of the two types, flat saddle key and the hollow saddle key. In the flat saddle key, the bottom of the key is seem to be flat, means that is in connected with the on the match with the surface of the shaft, and that is shaft is flattened. If we show in the figure, in the you should observe here, and it can be used for the light loads in the flat saddle key. If you take the hollow saddle key, there will be a concave surface is matched with the surface of the shaft. This is known as the hollow saddle key, and the dimensions of the key are width of the key and the thickness of the key. This is known as flat saddle key. The length of the thickness of the key can be taken as W by 3, which is equal to D by 12 here. And this key will be used for the light loads we are using. And the next one is the sunk key. These are provided half in the key of the shaft. Just we should observe in the figure itself here, half of the key is in the shaft and the half is in the hub here. And this is another rectangular sunk key, and the taper is provided in the form of 1:100 on the top surface of the hub here. And the dimensions of the key are the width of the key W and thickness of the key is the T here. The usual proportions of this key are the width of the key W equal to D by 4 and thickness of the key T is equal to 2W by 3, which is D by 6, where D is the shaft diameter, and the key has the taper 1:100 on the top side only. And the next key is the jib head tapered key. So it is a rectangular sunk key with a head at one end, and it known as the jib head, just we shown in the figure, and it is provided to facilitate the removal of the key. In the coupling, if you want to remove the entire assembly, it is very difficult, so that once you remove the key here, and the remaining parts can be easily removed. That is known as the jib headed tapered key here. And in the jib headed key, this the key is provided, then the shaft here, these are the forces are acting on the key in the hub and the shaft here, and the angle is making an angle 45 degrees with the rectangular surface of the key, and the height of the key is 1.75 t, and width of the key is W here, and its dimension is 1.5 t here. Thickness at the larger end is the D by 6 that we are taking here. These are the usual proportions of the jib headed key. And coming to the feather key, a key is attached to one member, as you see, which is attached in the driving shaft, okay, shaft here, and the other is also projected on the hub surface by fixing the set screws here. These are known as the feather keys here. And this allows the free axial movement of the hub. This permits the axial free movement of the hub. That is the advantages of the feather key. And the next one is the woodruff key. It is an easily adjustable key, and it is a piece of the cylindrical disc here, which is having a segmental cross section, which is placed in the shaft here, and its projections are also placed in the hub here. And this key is largely used in the machine tools and the automobile construction parts we are using. And the next one is the round key or the pin. The round keys are shown in the figure, which are of the circular in section and fit into the holes drilled partly in the shaft and partly in the hub here. And the advantages of these keys are can be used for the low power drives we are using. That is the main advantages of the round key. And splines, these are the multiple parallel keys which are integral with the shaft itself. Generally the shafts are having the 4, 6, 10, 12 splines. These spline shafts are having the relatively large strength rather than the shafts which are having the single key here. And now coming to the forces acting on the sunk key. Generally the key is used for transmitting the torque from the one shaft to the rotor. The following two types of forces are acting on the key. The force F1 due to the fit of the key in the figure that you should observe. This is due to the tight fitting of the key in the shaft. And the forces produced in this key is very difficult to determine its magnitude. And the another force which is acting in the down here due to the torque transmitted by the shaft, these forces are producing shearing and compressive stresses in the key here. And the non-uniformity of the distribution which is caused by the twisting of the shaft within the hub here, and the forces acting on the key for a clockwise torque is being transmitted from shaft to the hub is as shown in the figure. The key is in the shear, just you should observe the shear plane, the length of the key and the width of the key is coming into the picture. Coming to the crushing of the key, the thickness of the key is placing a vital role in the area in crushing of the key here. And the shaft of the key, here is the shaft and this is the length of the key and the thickness of the key and width of the key. These are the dimensions of the, you have to see how the forces are acting on the sunk key. And the strength of a sunk key can be obtained by keys connecting the shaft and the hub, which is we have seen in the figure here. Here we have to consider the dimensions of the key. Let the torque is transmitted by the shaft, and L is length of the key, and W is the width of the key, and T is the thickness of the key. L and tau and sigma C are the shear and crushing stresses for the material of the key. Now due to the power transmitted by the shaft, the key may fail due to the shearing. If you consider the shearing of the key, the tangential shearing force acting on the circumference of the shaft can be taken by area resisting shear, that is nothing but the L into W, which we have seen in the figure, and the tau shear stress. So the torque emitted by the shaft, which is given by T equal to F into D by 2, where F is the L W tau into D by 2. This is the equation for the torque transmitted by the shaft when you consider the shearing of the key. If we consider the crushing of the key, the tangential crushing force acting at the circumference of the shaft is given by F equal to area resisting crushing and crushing stress, which is given by L into T by 2 into sigma C. Therefore, T equal to L into T by 2 into sigma C into D by 2. Therefore, the key is equally strong in shearing and crushing. So, we have to obtain a relation W by T is equal to sigma C by 2 sigma. From this, we can say the crushing stress in the key is 2 times the shear stress. Then we are using the square sunk key here. And the shearing strength of the key, these are the equations we are using. Total torsional shear strength of the shaft, which is equal to pi by 16 tau and d cube. So if you equate the shear strength of the shaft to the shearing strength of the key, we are getting the length of the key as 1.571 times d into tau and by tau. Though the effect of key base, we have a relation based on the experimental results by Murray. E is equal to 1 minus 0.2 into W by D minus 1.1 into H by D, where E is the shaft strength factor, and W is the width of the keyway, D is diameter of the shaft, H is depth of the keyway, which is taken as the of the thickness of the key. So if the keyway is too long and the key is of sliding type, then the angle of twist K0 can be increased in the ratio K theta is equal to 1 plus 0.4 into W by D plus 0.0 into H by D, where theta is equal to reduction factor for the angular twist. These are the relation that we are using in the keys. And after that, we are using a small problem. Design the rectangular key for a shaft of 50 mm diameter. The shearing and crushing stress for the key material are 42 MPa and 72 MPa. Width of the key, thickness of the key T is also given. So the rectangular key can be designed by considering the shearing of the key T equal to L double G into tau into D by 2. After that, you substitute all the relations, you are getting the T in terms of L Newton mm. So the torsional shear strength of the shaft is given by T equal to pi by 16 tau D cube. You substitute all the values, you are getting 1.03 into 10 power 6 Newton mm. If you divide the equations 1 and 2, so that from the length L equal to 61.31 mm. If you consider the crushing of the key, we know that crushing strength of the key is equal to L in T by 2 sigma C in T by 2. And by substituting all the values, you are getting L equal to 117.7 mm. If you take the larger of the two values among the shearing and crushing, it is L equal to 117.7. We will take it as 120 mm. Thank you for patient listening. Thank you very much.